All right, welcome back. I don't know what happened. There's not many people in class today. Maybe they'll come in later. How was the homework?
Hard.
Yeah, hard?
Two problems.
Was it hard to come up with a hypothesis or hard to come up with a test?
I had a hard time coming up with the numbers that I would want my test to compare to. So doing the math to catch the number of misses.
Yeah, okay, for the last one. Yeah, the last one is really hard. Let me close the door. So I thought we'd just quickly go through the homework and what I think are the correct hypotheses. I mean, there's probably different ways you can formulate the hypotheses. And I can suggest some experiments that would have, or some good tests, predictions and tests. All right, so, for the first one, so here we had a for loop that, we should probably look at the code. Right. Okay, so here's a for loop that counts up a local variable, and when you compile it with optimization, the whole thing just disappeared. So the right hypothesis is that the compiler eliminates code that it knows doesn't have any effect. Right? So if you just get rid of all of this stuff, the program will perform exactly the same thing from the outside, except for performance again. Right? The program will run faster, but that's okay. The optimizer is supposed to make the program go faster. So correct hypothesis is just that it removes the whole thing. It's not that it pre-calculates anything, which is another possible thing it could have done. And so, wow, it gets noisier when the door is open. The door is closed. Okay, so how can we test this hypothesis? Well, why don't we keep the code, but use the result so that the result is actually important. So one way to do that was to printf the count. Right? If you do that after, now the compiler cannot just remove this code anymore. So now, and you would find, if you look at the assembly, that's a good test for it. Look at the assembly produced. If you print out the value count, then you'll see that it actually generated some code for this loop. It wasn't much of code, though. It was just an assignment, I think. It probably assigned like RAX to, what is that, 100 million or something like that, right? But now it's not eliminated anymore. So the hypothesis is it can eliminate anything that doesn't have any effect. And if it does have effect, then the code comes back. Okay, so that actually any questions on that? Yeah?
Yes. So now, when we add in the print statement, it takes a little longer, but it's still within like the noise floor of the time command.
Yeah, the problem is the print takes a long time compared to the other stuff we're doing. So the measurement is going to get really noisy. If you just look at the print of, if you just look at the time, of code that has one move and code that doesn't have one move, yeah, that's less than a nanosecond. We don't get to measure that sort of thing, usually. In fact, it takes way more than a nanosecond to just see what time it is.
Okay. So what kind of evidence would you have been looking for?
The right evidence for this one would probably be to look at the assembly to see what the compiler, so we predict that the compiler removes things or doesn't remove things. Right? Another thing you could have done is not print it, but assign it to a global variable. So the compiler doesn't know anymore. In the case of a global variable, maybe it's not used, but that's really hard to determine because you're only compiling one object at a time, and the compiler doesn't know about threads and such. Okay, any other questions on that one? Yeah.
If you print like after the for loop, then I think I was seeing the for statement get like optimized like to just like compute the count.
Yeah, exactly. Right. Yeah. So
then that looked really similar to the global, setting the variable global thing. So
yeah.
I couldn't really see much of a difference between question 1 and question 2. Because
Yeah, they're very, very similar. So I think the hypothesis, if is there a weird echo now? I think the microphone is on. Is there a microphone? Yeah. Anyway, are you hearing it too? Is there?
Yeah, it's on.
I could turn mic off. Is that better?
Yeah.
I can't even see the mic. Okay. Anyway, so for number 2, so this was actually, I kind of put number 2 in there as a hint for number 1 as well. Like if you tried number 2, you would notice that this, while it doesn't print anything, it actually produces code. It's not much of code, it's just this assignment of count equals that. So we can't use the hypothesis that the compiler eliminates useless code anymore, right? Because it doesn't. Well, it doesn't know that this code is useless, so it can't eliminate this one. So the next hypothesis here would be, well, if we can compute the value of this expression, or this, is it a statement maybe, at compile time, we'll just do it then. So the compiler will try to simplify expressions that can be computed at compile time. So a good that's a good, I think that's probably the right hypothesis. Many ways to put it. What is a good experiment? Well, we could try to change this thing so that the compiler doesn't know anymore. Like the compiler can't produce a value at compile time. So what can we do? I think one thing that probably some of you tried was, let's replace this one with let's say an input variable, input value from command line. And then you'll find that it still produces some pretty interesting code. It probably does like a, let's see, it assigns count to whatever the numeric value was of your input. So it got rid of the loop anyway. So how can we make it not get rid of the loop?
You can change count plus to something like count star equal to 2 or something like that.
Yeah, so if you do it count star equals to 2,
Or star equal to 3.
maybe it could still do it, because that's a pretty simple expression. But yeah, I think I had a suggestion in there, like, oh, if you put this, that's a pretty complicated thing. The compiler could probably have a case in there. You're a really clever compiler writer, they might figure out a way to simplify this thing too, although we have also limited size of the count value, the integer that's holding count. It's going to get really hairy to do it right. But with enough code in the compiler, you could do it. Of course, nobody's going to need it. So now you have like 10,000 lines more code in the compiler for no reason, and so it doesn't end up in any compilers. Can I ask, how come so many people showed up late to class today? Is there something special going on? No? Okay. Okay. All right. So, right. So that's one way to do it. We can change the expression to make the expression complicated enough. Or maybe we could have something in the loop that reads from a global variable that the compiler won't know what the value of the global variable is. There might be ways to trick it, right? So here we would say, once the compiler cannot pre-compute the value at compile time, then it would leave the loop in place, which it did. Questions on that one?
There was another observation that in case of the optimized version, it just read the global variable variable before the loop and route it after the loop. Well, in the simple code, it read and write in every iteration.
Oh, yes. So generally speaking, unoptimized code will take every C statement and replace it with some dumb series of assembly and not worry about all the other C statements. And then the optimizer will be in charge of kind of removing the useless assembly.
I was thinking maybe they read and write in every iteration to introduce some latency.
Let's see, might introduce some latency. Oh, you're talking about a hypothesis. Yeah, so of course, it's right that all that reading introduces latency. So your hypothesis is that bad code runs slower. That is the correct hypothesis, but it's probably not the right answer for this. Yeah. So generally speaking, the job of the optimizer is to get rid of that sort of thing, of course. And I think the hypothesis we're looking for is what is the optimizer up to? Like, how was it able to make it this much faster? Right? So, but did you observe it with the loop still in there?
Yeah, I mean, if the loop's not there, then there's no point. Then once I make it execute the loop, then in the optimized version, it reads the count before the loop and route it back after the loop.
Oh, I see what you mean now. So even with this stuff in there, we get we still have faster code than we had with the unoptimized. Okay, I'm sorry. Yeah, absolutely. And I think that brings us to the third one. But I'll take another question first.
So like when I ran 2, the global variable, like my compiler seems to get rid of the loop anyway.
Just a global variable, yeah. There's no need to keep for 2, there's no need to keep it.
Like the output of both of them look like exactly.
Yeah. So let's see. Go back to the code. Right. So for 2, yeah. So the optimizer, even in this case, it doesn't care about multithreading. Right? It doesn't care about, what are all the various numbers that count could take on here. It's just like, what's the output? When I'm all done with this, what was the result of my computation? And that also brings us directly to number 3. Any other questions on 2? Yeah.
So for that case where you do the divide equals 3,
Yeah.
I definitely thought that was invariant, and I was reading online that the compiler can't tell what the decimal amount is from dividing from before. That's why it keeps it in the loop.
Okay.
Why is that the case? I thought it would definitely get optimized away.
So I don't know that it's impossible to simplify that thing, to optimize that out. I just tried a whole bunch of things until it got too complicated for the compiler, and I figured it's not quite fair to expect you to do all that, so I left the example in the homework description. Yeah.
Yeah, no, I was looking at that one case and I was kind of boggled by it. But I guess it made sense. I found a Stack Overflow link that I added to my report.
Okay. Great. Let's see, what did we say here? Oh yeah, so the divide by 3, I mean, count is an integer, but you get all this hairy modular arithmetic going. Like, it has to deal with the fact that the 64-bit is also limited. And so now this divide by 3 in the middle of all that, it seems really complicated to get it right, and maybe unnecessary to worry about it as a compiler writer. That was my hope, and it kind of paid off. We could have gone further. Like, we could have gone with XORing some stuff or flipping a bit here and there. Like, at some point, the compiler would give up. Right? Okay, so in this 3, we just stick a volatile in there. All right, so I think it was the same as 2. The only difference is we say volatile. So volatile means that count could be changing on its own. There's another observer, and maybe mutator too, of this variable. So it's not just the value that matters. What matters is also the time at which we read it and when we write to it. The original intent of volatile was for I/O devices. So you might have, say, the keyboard writing directly to your memory buffer, let's say. No, that's a dumb. Okay, we don't need to worry about I/O devices. Let's just worry about I/O. So you might have the operating system writing directly into your character buffer. And so whatever you're pointing at could change. Even though you didn't change it, your buffer might change. So you can't just rely on, last time I checked, it had this value. It's not necessarily going to have the same value anymore. So that's one direction, and volatile goes in both directions. It's also, someone else might actually care about what you're doing with this value, not just what it's going to end up being. So I think a good definition of volatile, and maybe a hypothesis for what does volatile do, right, is it prevents the compiler from sort of optimizing out any access to this memory. So if you have a read or you have a write, it's going to be there. There's going to be a move to or from that memory address at the end. So in this case, I actually don't remember what it produced. If it produced an ink, perhaps, or a read and an ink and a write. There's both. But you could imagine producing useless code. So this one actually generates a new value for count. Right? But what if you set this count equals to 1 all the time? You just set count equals to 1 100 million times. Right? That's if volatile means you have to keep every one of those writes, it's still going to be there, even though the other parts of the optimizer will say this is useless stuff. We can throw it all out. So I think that turned out. If you set it to 0, I think you'll see a whole bunch of let's see, ones probably. Doesn't matter. But you will see a whole bunch of moves to memory in a loop. Okay, so volatile is a really handy keyword when you're writing multi-threaded programs. If you don't do that, the compiler will do things like, oh yeah, let me keep count in a register before the for loop, and then I'll just increment it in a register, and then I'll write it back after. Because it produces the same output, we're not losing the final value. That's all fine as long as you don't have some other thread looking at count, hoping for it to become, say, power of 2, in which case it's going to, print surprise. Or, I don't know. Like if you have threads that are interacting through the values of variables, you really need to make sure that the variables end up in memory and aren't just sitting in your register. I think it's maybe worth noting that this value, of course, it has an address. Count lived has a specific address in memory. It doesn't always, like that current value of count. For volatile, you can't even trust, when it's volatile, you can't even trust that whatever's in your register is the current value of count. Because someone else could have changed it between your previous read. So if you actually need to know that it hasn't changed, you need to do something atomic, right? Then there's two choices. We can use a lock around it, and then no one else can change count as long as they also acquire a lock naturally if they're trying to change it. Or you can use an atomic increment. There's some special instructions in x86 that do it without locks, but it's kind of a hardware lock instead. No big difference. Right. Whereas if you write, if you have a local variable, say int count over here, or just int I, its location is actually undefined. We don't know if it's going to be on the stack, or if it'll be just in the register, or maybe not at all. Like the variable may not even exist because we're not really using it for anything useful. It won't even be there. In the case, say we had a loop here of 10 I, and we're not using I. Well, the compiler could decide to just unroll this and make 10 plus pluses back to back, and then there's no I anymore. Local variables are really kind of nebulous in that sense. And I don't think that a local variable can be volatile, but I could be wrong. One thing that's really funny about that is, what if you try to pass, say, a pointer to one of your local variables to another thread? You know, you could write, say, assign a pointer, a global pointer, say, this pointer points at my local variable.
A function?
In a function, yeah, you could do that. Like,
But then you won't be valid anymore, right?
that'll be terrible, yeah. So you could write like global ivar equals address of ivar, right? Oh, yeah, myvar being a local. It's a terrible thing to do, but the compiler will now make sure that myvar is in memory. Right? It'll have a stack, an address on a stack, because you can't take the address of something that's in a register. So that's fine. But of course, as soon as you leave your function, it's now pointing at some other garbage. Yeah, so definitely not recommended. You can safely do it if you call a function from your function, right? So you have this struct, big struct, right, on your stack. You allocate that as a local variable, and then you can pass in, oh, well, we probably should have a name for it too. That's just here. Okay. And then you could say, oh, f the struct, just fine. Because your function will be alive longer than f, and so it's okay. In C, there's no, like, nobody checks, really. The compiler tries a little bit, but it's kind of fake. If you do it in Rust, then it'll keep a very tight leash on what you're doing. It would be completely impossible. You might be able to pass in a reference to the struct just fine, but it'd be completely impossible for f to assign that to a global variable. That'll just never happen. Whereas in C, you do what you feel like. I think there's advantages to both, and I still kind of feel like we should maybe try a Rust assignment or two toward the end, but it's also really hideous experience, so I'm not sure. It's really hard to get something to compile. So we'll see. Maybe we can make it optional. Okay, so was there any other questions on 3? Oh, I promise we'll do this quickly. It's not really going quickly. That's okay. Okay, so what about this one? Was this hard? Number 4? Oh, that's pretty easy. All right, so we're whenever you access some memory, it pulls in 64 bytes because the cache line size is 64 bytes. So now it's sitting in your L1 cache. Anytime you've recently accessed memory, it'll be an L1 cache. The next time you access the same cache line, it'll take 3-4 cycles. So in this case, it's 3 or 4 cycles per each one of these increments, and in this case, it's another cache miss. Depends a little bit on all the other stuff you're doing in the code. Sometimes the CPU feels it's not very busy, and it'll go and try to prefetch something. So it'll say, okay, yeah, they've been accessing like 64, 128, 192, 256. Let me try 300 and I forget the next one. So it'll do this. It's called stride fetching. So that's one way you can do it. Or it says, oh yeah, so they wanted that cache line. Let me get the other one. If there's, it's called a pair prefetcher. They keep these 128 byte pairs. So if you access one of the two, it'll sometimes go and fetch the other one for you, because probably you'll want it later. So that's okay. The prefetcher will never prefetch anything unless the memory bus isn't busy. Let's see. Yeah, right. If the memory is busy, it won't prefetch anything because it's much better to do what the user says than what we think the user maybe will want later. So if cache stress was busy doing other things, doing a lot of computation, then we would see big prefetcher impact here because we're doing extremely regular fetches. But in this case, we're really stressing the cache as it is. Okay, so I think what's a good hypothesis? Well, the 64-byte cache lines, I can't think of how to formulate it right now, but hypothesis is that memory is fetched in 64-byte chunks. And subsequent accesses to the same 64 bytes are fast. Okay, so then we could predict that if we access every 2 bytes, it'll go maybe half as fast about. All right. If we do every 32 bytes, it'll be almost as slow as the 64 one. Right? Not quite. So that's one way, but the timing is a little tricky, right? Because there's constants involved, and we don't know what the constants are and such. A better way would be to look at the actual number of cache misses. So if you use perfstat, you can just ask for L1 cache misses, and you'll see. So now you can predict, because we haven't done this yet. We predict there will be 64 times more cache misses for this line than for this line. And so you measure it with perfstat, and that's it, and you're done. Of course, it's always better to do more experiments, right? Could be that there's some other explanation that also makes the same prediction, and but at least it will help a little bit. That leads us to this last one, which is really hairy. So I sent out this comment about the associativity a couple of days ago, I think. And I thought that you would have gotten that from your architecture class, but associativity is kind of an obscure topic, so that's not so important. In any case, the hint was it's got something to do with cache associativity. And should we talk about how this associativity works, or yes? No? Okay. No, no no's. 2 yeses. Class engagement is at a peak. Okay. All right, so briefly, the point of this cache associativity is in an ideal cache, you would have any memory address that you want to cache can go in any part of any line of your cache. So in a 32 kilobyte cache, you have 512 cache lines, right? Every cache line being 64 bytes. So now you have 512 different slots you could put this 64-byte cache line in when you need something. You evict the oldest one in this big cache, and you put your new cache line there. That would be an ideal cache. Those caches are very expensive. There's a lot of extra wiring in there because you need to figure out which one is the very oldest of everything in the cache, and probably, yeah. I'm not the chip designer, so I don't know. But those don't really exist, I think, or if they do, they're unusual. The worst case extreme is the other way around, where which cache line you use is just based on the address. So, let's see if we can draw an address. Okay, so the first one doesn't need a drawing, I think, but so here's our 64-bit memory address. We have like bytes within the line are 6 bytes offset, let's say. And then the rest of it, Right? It's 6 bytes because it's 64-byte cache line. So those 6 bytes, they just say which byte within the cache line are we interested in. We're not going to use that to determine which cache line. And then we have all of these. Depending on how you count, it's 42 or it's 58 remaining bytes of the address that, not 42. Yeah, it is, okay. 58 to 42. That says like which cache line in the entire memory, like which 64-byte chunk of the entire memory range are we talking about here. So how do we divide it up? Well, one way to do it, and that would be, you say, so we had 512 cache lines, right? What am I? Bit. Thank you for correcting me, nobody.
Isn't it 5, right? 0 to 63 is 64 unique values. Am I messed up?
2 to the power of, you're gonna need
Power
6 bits.
is 64, right?
Yeah.
But all the ones, if everything's turned to 1.
That'll be 63.
5 is 63, right? And then the 0.
Oh, so that's 64, and that's what we want.
64. So there's 64 unique values in 2 to the 5 in 5 bits.
Nope,
Okay.
to the 6.
Well, I missed that. All right.
It's all right. Okay, so we, so these are 64. 2 to the power of 6 being 64 here, and then, so this one says 9-bit cache line number. All right, so that's one way that you could do it. Sorry about the small font. So we just look at the lowest, the next 9 bits to say which cache line are we going to use. This is super simple. Right? We know exactly which cache line. If we're looking for the content of some address. Now, if we're going to use a cache, we're going to have to look in the cache first to see if it has the contents of that address. All right, so the cache is going to have to say first which address is it that which cache line are we keeping here, and then the contents of the cache line. So then the question is, if you have 512 lines, for a fully associative cache, you would have to check each one of them one way or another, maybe with some clever data structure, who knows. But you'd somehow have to check all of them to see if any of them has the value we're looking for. In this case, we look at these 9 bits of the address, we know exactly which cache line to check, we see if is it the right address that it's representing at the moment, if so, return the value, otherwise move on. So that's really fast, yeah.
So this is a direct math cache?
I think that's the term, yeah.
So like, yeah, so it's just the last 9 bits, or just some 9 bits of the address that maps to the cache line?
I would think it's gonna be the last 9. Those are the ones that change the most. It would be terrible to use, say, these, because they're all gonna be 1s or 0s all the time. So the reason I said, what did I say, 42 or 58 is that we talk about 64-bit architecture, but all of these Intel machines, they actually have a 48-bit address field. So you give it 64 bits, but the top 16 bits, they're all 0 or all 1, depending on what the next bit is. Like the highest, the 48th bit, which value is that? If it's a 0, then all the other ones above are 0. They call it canonical canonical something. And it's just, it's too expensive to have extra 16 bits support in your CPU when nobody would ever need 2 to the power of 48 address space anyway in current machines. Of course, when you get to bigger machines later on, maybe we'll need it. And then the architecture, the instruction set supports it, but the architecture can support it later. That's sort of the idea. Okay, so anyway, the problem with this is that now there's only one place where for any given memory address, there's only one place where it could be. So that's nice, that's fast. But what if you accessed another memory address that fits in the same line just recently? So in this case, let's say 512 cache lines later, right? There's 5, so it ends up being like you divide up all of memory. That's address space now. Now we're looking at memory. So we have 512 lines, or actually let's call it 32 kilobytes, right? So it ends up looking like this. All of memory ends up looking like that. And then, oh, you make an access here at the very bottom of the lowest part of your 32 kilobyte chunk here. And then you make an access over here. Now that's actually the same cache line. And then you do the next one and the next one. So now every time you go to the next 32 kilobyte step, you end up evicting the previous one, which doesn't really matter if you're just going to blow through the whole thing. Then the cache is of no use. You only visit it once. But what if you go around and around? Right? Now it's a problem. So now you have a 32 kilobyte cache, and you're visiting 2 cache lines, but you're getting a cache miss every time. Right? That's ridiculous. But that's cache associativity. So now this is a direct mapped or a one-way associative cache. So, okay, it's only a problem if you actually do these accesses 32 kilobytes separate, right? If it's 33 kilobytes separate, nobody cares anymore, because now you're basically using up the whole cache. So it's only when you're doing these very well-aligned power of 2 kind of accesses that you have issues. So we don't need to worry so much about it, but we probably should deal with it one way or another. So the way they decided to do it is you have a degree of cache associativity. So we say, well, maybe for each one of these chunks, we have 2 slots. All right. So we make little buckets of 2 slots or 4 slots or 8 slots, and the address can be present in any one of those 4 or 8 places inside the bucket. So, okay, so then it ends up being like this, and I think it's like that. So for 8 cache, okay. So for an 8-way associative cache, 512 divided by 8, 64. So this is 64. Let's see. So now this is like, I like to call them bucket number. I think there's another word for it. I don't remember what it is. Sorry? Set? Set. Okay, good. Set number. Okay. Right. So I think it works like this. So there's a little gap here. I'm not sure it matters. Okay, let's do it like that. So now there's 64 of these sets, and in each set there's 8 slots. So you can do like this one, this one, this one, this one, and all of them belong in the same set, but you've only used up 4 slots. And you keep going, 5, 6, 7, 8, and now that set is full. And for the next access, now you end up evicting the least recently used, being that one. Right. So that's what we're seeing in this, in the beginning of this exercise. Let's see if I can run this. Do I have it here? What is happening? Let's try it. All right, so in the beginning, so we're going through a, so 1 megabyte area, right? So we have 1 megabyte that we're representing. So it's only going to give us trouble in the L1, like the L3 can hold the whole thing. Is that what we did for the last one? Oh yeah, okay, that's fine. Okay, so after a while, as we increase the step size here up to the size of the L1 cache, in the number of, basically the size of the L1 cache. Then now we start having misses, even though, let's see. Yeah, okay, so we're going around 1 million of these, right? So here we're visiting, how many is it? 256 of them, right? So that should fit easily in the cache, in the L1 cache. 256 different lines, we have 512. But because of the cache associativity, they're all hitting the same set. So they're not fitting, like it's starting a little earlier, but they're not fitting in that set, so it's not actually in the cache anymore. Whereas with the smaller steps, it all fits in the cache. I think it probably fits in the L2, not in the L1, because it's relatively large. Okay, but then as we go even further down here, now we're visiting 4 lines. 4 lines back and over. So these are all in the L1, and that's why we're going so very fast, because they're always all in the L1. Okay, so that's a very long hypothesis. I think one way that we can test this hypothesis is change the size of the array that we're iterating through. As if you grow the array, you're going to have more misses earlier on, I think. It'll get slower earlier on, and it'll take longer before we get down to the slow speed. I think that's it. To the fast speed again. I think that's right. I want this times 2. I'll have to ask Bash for help. Okay, so now our problem is starting at 512. Okay, it wasn't that convincing. And then it took longer to kind of get the relief, because we're hitting 8 lines now instead of 4, because it was a bigger set. Maybe we do one more size. Yeah, so now it's getting really bad earlier on, and probably we'll never, we won't see the total speed up anymore. Yeah, so that's probably hiding away in the L2, not in the L1 cache. Okay, questions on this one before we move on? Yeah.
What if we change the multiplication factor for the interval instead of 2, we increase it with a multiple factor of 3 or 4 and see the effect on the execution time? Because in that case, mapping would change as well, and we would observe a different pattern and like associated mapping would change.
I'm not understanding the multiplication factor. You mean here in the bash command? So you would, oh, I see. Yeah, so then you get, that's good. That's a fine hypothesis. And you'd say, so in this case, that's a fine test. Your hypothesis would predict that now they're not going to be hitting the same cache lines all the time. So the associativity problem goes away if you do times 3. Does it?
It doesn't, like, it says that instead of 4096, probably you had more execution time around 1000 something or so. You can try it right now as well.
I should step back to the million here. Yeah, I made another one where I'm accessing random pages instead of like a million random ones instead, and that doesn't have this issue at all. Of course, with times 3, there's still some regularity to it, so that's probably having an impact. Actually, this was not very interesting. Times. Yeah, I suppose it's, yeah, this is, right, okay, so it actually wasn't a very good test. Reason being, we're still doing very regular accesses, and we probably end up on the same cache line over and over. Like not as often, but after a couple of times around, you probably end up on the same place, perhaps. If you run it with, if you try to access completely random lines, you'll see it's completely uniform access times. Okay, so any other questions on this one? Right. You know, don't think of cache associativity as this crazy boogeyman now. Right? You're probably not going to run into it again. So it's not a good hypothesis, generally speaking. But if you can't explain why you're having so many L1 cache misses when you're just accessing a very small set, and it's some array of relatively large structures, and you keep accessing them regularly, okay, maybe, right? But it's not a problem you would run into very often. Okay, so now I was thinking we would go back again to our friend, the closest line, and see what we can do to make it run quickly and correctly. There's probably many things we can do, but let's try by just doing some explicit pthreads programming, and that also gets us into a little refresher on how that all works. Yeah, I haven't made the third homework yet. Just planning to do it today or tomorrow. What do you think? Shall we do? We can do either a more real program. Probably I'll try to dig out some real program that doesn't run fast enough, and we'll try to make it faster. Or we can have a toy program and start with multi-threading sort of things. But keep in mind we'll have multi-threading later on as well, so it's not like it's going to be the only multi-threading homework. Real program, multi-threading, okay, that was easy. All right, it makes it harder for me, but I'll find something. Okay, right. Here's our favorite. So I wanted to get rid of this OpenMP now. Did you have a question? No. Oh yeah. Okay, so I think we'll do it. Let's see, I need this saved correctly. Yeah. So we'll just make this, we'll just parallelize this line store closest. We won't worry about the rest of the code for now. And I think last time we ran it, it took, oh yeah, it took 2.5 minutes the last time most of you had left, but it ran, that's actually the same time it took to parse everything single-threaded and then do the comparisons. So with 64 threads, it also took 22 minutes with, 2.5 minutes with all of the optimizations in place. So I think that's an important message. Just piling on threads doesn't necessarily speed up your program and can make it very much worse as well. So it's not a bad idea to try to make your program fast single-threaded first. It gives you a good understanding of what the program really does. And then maybe there's an opportunity for properly parallelizing it. It's not always the case, but oftentimes you can find, at some level, you can find a way to parallelize it. Maybe it is, oh, different users should be using different CPUs. Maybe it's not. We should split this CPU for a single user, we should split it into 64 CPUs. That could be too much coordination overhead. It all depends on the case. Same as always. And so that's the time. That's, what is it? Is it this task set thing now? We probably should figure out which one we belong on. Try it on. There it is. Probably 16. 24. Right. Okay. So we should be running this on Core 8. There it is. Okay. Now we have a warmed up cache too. Good. So there seems to be two opportunities for improvement. So, but let's focus on the user one first, and then, excuse me, then we'll see if we can do anything about the system stuff as well. After all, that's about 30% of the runtime. So we'll just do it in here for now. So in this case, we'll have to actually maybe we can do a range. Right, okay, so this will at least produce for us the min within some range. I was thinking we start a pthread for each range, we split it up into some pieces, and then we kind of try to join them together. So we'll have to can do it like this. So I guess we're going to have to worry about how we get the minimums from the various threads. Like I'm going to run 64 threads now. They will each produce a different minimum, and after that we have to find the minimum of those 64. So let's maybe not worry about that at this exact moment. It's possible that we can get the min line actually back this way. I don't remember how join works in that regard. We'll see. But let's start by just running some threads. So we'll do 64 of them. Let's maybe say there are two good reasons to define constants like this. One is, of course, you're going to use them in many places, and when you change the constant, it'll change everywhere. That's great. But it's also a great way of avoiding having to document your code, right? Because, so you could say, oh, yeah, 64 here is in a comment, you could say that's the number of threads, but this is much better. Right? Ideally, you don't want any documentation in your code. The code just reads like English. Right? Yeah.
You can also change the define when you're compiling it by passing it in a flag.
Yep, if you like, yeah. Okay, that was just an aside. Oh yeah, okay. So we're starting to hit trouble already. Good. Let me see what create does. Yeah, okay, so we want a thread and then some attributes, which we don't care about. The start routine, that's the problems. And then there's an argument, which is a void, unfortunately. So we'll just go like that. It's a void star. See this? So the routine we have to run, it takes a void star argument, which ideally would be like a pointer to a struct with all your parameters, something like that. And then it returns a void star. In fact, I think you may get that back when we use pthread join later. I'm not sure about the return. So we're going to have to change this a little bit. So I guess we'll stick the point in here. And then the start and the end, that doesn't really fit because we have to take a void pointer, but we can make it like this. And then we'll have to compute this down here instead. So, okay. That's about it for that, and then we want to probably join them all in the end. I don't know if it takes a pointer, let's see. No, it doesn't. And the return value, ooh, that's really nice. That's really nice. Okay. All right, so what's going on? Let's see. Has anyone not done pthreads programming in the past? Okay, 2, and then there's like 30% of the class who isn't admitting it. So we're gonna go with a quick intro. So pthread creates operating system threads. This is the only way that you can run a program on multiple cores of a CPU. So there's all sorts of other funny sort of tools or libraries you can use to get parallelism in your code, but in the end, everything relies on operating system or kernel threads. Each thread is basically a bunch of register values. That's the main thing. So they all say like, oh, my values, my RAX had this, my RBX had this, and so on. That's what a thread is. Now, you can run multiple threads on one core, but only one at a time. So you get a context switch. Context switch means there's an interrupt or something, the operating system takes over, and it takes all of the old register values from your running program, which could have been running anything at the moment. It's suddenly interrupted, it stores all of those register values in a little struct in the OS, and then it sticks in a bunch of register values from another thread that wants to run in the registers and returns control to the program, to user space. So now suddenly it's running this other program for a while, and then you switch back. If you're going between just threads, that's all it is basically, just switching a bunch of register values. If you're also switching between processes, you also have to change the page table, which is a little bit hairier, but not much. It takes longer. Okay, so if you want to run a program on 2 cores, well, 2 cores, that's 2 sets of register values. All right. Each one of them is running some instruction at any given time. The other one has no idea what this one is doing. That's the general execution model of a multi-core machine. So they're all very independent. The only thing they have in common is shared memory. So if you try to write to some memory address, if another program is reading from that memory address, they will see that you made a change. They have no other way of communicating. Okay, and that's especially true for user land. If you're in the kernel, there's some other things you can do. You can trigger some interrupts. You can make things happen a little more, but user programs don't have access to that sort of thing. So if you want your threads to communicate, the only thing they can do is write a value to memory and then hope that the other thread will go and look at that memory address to see if it's changed, or to use that value. Okay, so to create a new thread, you say pthread create. That at some point ends up calling a system call called clone. So now suddenly you have two threads, the one that we were running at the moment, and then another one that has the RIP, the register, the instruction pointer is pointing at this, right? Whatever function you passed in. And then it has one argument on the stack. There's one more thing that happens before it starts running at that. It puts something on the stack. It basically makes it look as if the function thread exit called the function you wanted to run. So by the time you return from this function, it's going to return pretty soon. When that returns, it returns out to a function called thread exit, which called it in the first place, but it didn't really. When thread exit is called, that thread is gone. Or when you return to thread exit, that thread is gone. The OS will clean it up. But the only time that it really cleans it up, like whenever all the state is removed and so on, is upon pthread join. So when some other thread calls pthread join on the thread that died. Pthread join is a blocking function. Create, it just goes immediately. You don't know which one goes first. Like, does this one start running, or do we go to the next one around? There's no order implied. It'll just go. But in this case, at the same time, we have basically 64 threads running at the same time suddenly, and our own. And we don't know which one's running. If they're all running at the same time, or maybe some are waiting for something else, there's no order whatsoever. It looks like, oh, we create the first thread and then we create the second thread, but the second thread could easily start running before the first thread. Okay, so we want to worry about race conditions there already. And then on pthread join, this parent thread here will stop until thread I returns from this closest range. Calls thread exit. Thread exit is a system call. Inside the OS, there's a little bit of coordination between the various threads, and eventually it'll return, and we collect one after another. So here we should have, and why don't we do this now? Got a local minimum line. Okay, so because this is the only way to create threads, you have to have kind of a generic function for it. The function that we call is always expected to take one argument, a void pointer just meaning this is anything, right? And then return a void pointer, which is anything. But they're pointers, which is nice. We know they're 64 bits. That's all we really care about. We can cast 64 bits of one kind to 64 bits of any other kind, doesn't make a difference. So here, I'm saying, in fact, I may have to, no, it probably will be okay. So here I'm passing in a pointer to an integer instead of a pointer to a void pointer, but it probably should be okay. Compiler maybe will get a little upset. And then same thing here. I'm supposed to pass in a void pointer as argument. I'm passing an integer. Probably will be fine. The integer will come in here looking like a void pointer, but then we'll use it as an integer, and we'll be okay. And then our start and end, we have to compute it. Let's see. You may have to do that. Okay, so I'll just say, how do we split this up now? We had there was a size of some sort. Line count, right? Okay. How does it go? Let me just move this up. Okay, and then that's not gonna work. All right, so this is the sort of thing you have to deal with. See, this is really a lot more complicated than this OMP, all right? So sometimes I think OpenMP is a really good choice, and it could have worked here too. It has some nice ways of combining the output here. We had this minimum. There's some ways that we can combine the outputs of all the various threads. We could maybe have done it, but we want two return values, and I couldn't figure out how to do that with OpenMP. And anyway, this is supposed to be the week where we do a little pthreads, so do that for now. We'll try to do a bigger review of OpenMP maybe next week or week after. Okay, is that gonna do it? Maybe. Of course, we're not getting a global minimum just yet, but that's okay. I have to link with pthread. That's the library for all those operations. And it probably wants an include. Hopefully that's it. Those are warnings. See, the compiler got a little upset because I'm passing in the wrong kind. Shall we fix it? Maybe we should. What do we do?
Cast it.
Cast it, exactly. So we're taking an void pointer, right? So I'm giving it an int pointer. I'm saying, oh, and by the way, this is actually a void pointer. That's okay. Actually, maybe we should make this long, right? Because otherwise, it should be okay anyway. But an int is shorter than a void pointer. It's 32 bits, so it could be that we overwrite something. That would really be really unfortunate. Let's do the same thing up here. What was it? And the compiler might not even allow us actually to pass in a 32-bit value as if it was a 64-bit. At least not a pointer. It seems a little iffy to do it on a pointer. What am I missing here? Oh yeah, here. Let's just, no, that's okay. This one will work. Okay, let's see what it says. My print. Oh, come on. What else? Oh, we're using P. I should be using this global P, right? Come on, what else? Did I hear race condition? What's the race condition?
You're just modifying global P.
I'm not modifying it.
You're storing the point. Oh, it's the same value point. Sorry. I
Yeah.
thought it was going to be different.
Right. They're all looking for the same point, different lines. Yeah.
Okay, but you're storing the result of 64 different threads into the same variable. Isn't it gonna be
I'm just storing it in here in a local variable, which is going to disappear. Like every time around, I get a new one. I'm just printing it out for now. And we'll have to compute the minimum of those in the for loop. Okay, so there's no race condition here because global P is assigned before we start all these threads. If I was to do it this way, then we don't actually know. Sometimes it will be assigned, sometimes not, when the threads start running. Okay, there were more warnings. Let's see. Pointer. Oh, okay. Yeah. Really? What's the problem here? Different size. Okay, fine. What is it now? Min line is also okay. I thought I fixed that now. Is there another one? 75?
Returning an integer.
Oh. Thank you. Oh, getting really close. And a different size. One more. These are all warnings, but so usually I don't worry about the warnings, but now I feel that, I mean, in class I don't worry about warnings because I want to move fast, but sometimes you get important warnings. And if we have 15 other warnings that are not important, we're going to miss the important warnings and it's going to be all over. So we better get this right. What was it? Here. So that's it. Okay. So let's see what it does. Okay. So we're getting a whole bunch of oh, it's printing something out. Oh, I see. Are we actually, what are we returning here? I don't think we're returning anything anymore. Yeah, that's nice. So see this? Saying the closest line is that. I didn't return anything. So it's just some garbage that's coming back. Whereas we probably should be returning, can start like that. Okay, yeah. Anyway, all right, so we have all these minimums here. Now we have to probably collect them all together. I don't know if we're going to do that now. Shall we? Well, maybe we have time. Let's just get that down too. And hopefully we'll have, actually, how long does it take? Ah, that's the print. It's the probably the main. So we've already done all the work. Let's see how long it takes without any printing. Doesn't look like it got, oh. I spotted an error, you didn't. Look at that, we're using one core. Let's try them on all cores. Threat. Actually, it's a little faster, isn't it? 700 instead of 7, what were we at before? 750? Yeah. I'm not going to do the final combination today, but let's just try this one more time. Yeah, oh. So those are, what am I doing? Minus F here. So it's a completely wrong place to put it. We want that task set thing. Here. Okay, so as a reminder, we have this. This is our machine. There's 8 on each of these, and our memory mapped file is sitting in these. So we want to be on the right socket, and now we're just going to use the cores from that one socket. See if that makes any improvement. Yeah. Okay. So we're down to 441 from 700. So that's good. The total user time spent, this is because we're multiplying by all the number of, all our 8 cores. Let me just try one more thing before we go. See if we use half as many. See if it makes any difference. Not really. Okay. So Good. Yeah. This changed the thread count. Oh, you would. I see. So that you have a little less coordination. Yeah, that's a good idea. So we should match whatever we asked for on the command line. Yeah. So because these are still very large numbers, milliseconds, the time it takes to switch between threads is maybe more on the order of 1 microsecond, 2 microseconds, something like that. So it wouldn't actually show up in these numbers. That's the only reason why that didn't help. But it was a good idea. Okay, so I think we're out of time. Yeah. We'll continue, we'll review a bunch of the various coordination stuff, synchronization, operations in pthreads next time. And try to go even a little faster. Have a good weekend.